We're starting a few minutes late here. And I think I better start so that we're not too late. It's my extreme pleasure today to introduce Dr. Benedetta Leuner as our next speaker. But before I do, I just want to make an land acknowledgement. I wanted to recognize that we live, work, and play and participate in the community on the unceded, ceded, and traditional territories of the 203 First Nations, along with 38 Métis chartered communities, each of which possess their own unique traditions and history right here on this land that we now refer to as British Columbia. And I recognize that many are not in British Columbia or in Canada. So I urge you to think about the Indigenous communities that on which you reside. We acknowledge the importance of the Truth and Reconciliation Commission of Canada's call to action, the United Nations Declaration of the Rights of Indigenous Peoples, and the BC Declaration on the Rights of Indigenous Peoples Act. In all of our work, we're committed to ensuring Indigenous women's rights to health and safety and the equal opportunity to participate in a manner that recognizes and respects Indigenous cultures and traditions. Today, I'm joining you from North Vancouver, because that's where I reside, which is part of the unceded homelands of the Coast Salish peoples and the traditional territories of the Musqueam, Squamish, and Tsleil-Waututh First Nations. And with that, as many of you probably already know, the Women's Health Cluster includes I think we're up to 260 members. We have many events, of which this is our last Women's Health Seminar series of this particular year. And we'll start again in September. And I can't wait to unveil the new lineup. I've got lined up some great speakers for you already. We, for those trainees among you, we do have some travel awards. I know no one's traveling right now, but we have very good success rates. So I urge you to apply for any awards that you see. There'll be some other ones coming up. I keep saying that we haven't announced any yet, but we will do so soon. And become a member. So you can't apply for these awards unless you're a member. And I need to thank the people that support our research. And today I will stop sharing my screen and allow Dr. Leuner to share hers while I introduce her. If you feel like following along in the conversation on social media, you can do so using the hashtag WHSS. I always get that wrong, but I'm pretty sure that's what it is. I would, in my introduction of Dr. Leuner, Benedetta, or Ben, she received her BA in Behavioral Neuroscience from Lehigh University in Bethlehem, Pennsylvania. After earning both her master's and PhD in biopsychology and behavioral neuroscience from Rutgers, she moved to Princeton University for her postdoctoral training, where she worked with Dr. Elizabeth Gould, who I also worked with in part of my postdoc. In 2011, she joined the faculty in the Department of Psychology at Ohio State University, which I am told there's a lot of new hires, and in particular one that I'm very excited about and who will be speaking in our next year's program, and that's Dr. Erica Glasper. She also has an appointment in the Department of Neuroscience and is director of a neuroscience undergraduate program. Oh, I didn't know that. In her research, Benedetta's primary focus is on the parental brain and behavior. Specifically, she seeks to identify neurobiological mechanisms that underlie cognitive, affective, and motivational function during motherhood, both under healthy conditions and in the context of maternal neuropsychiatric disorders. Over her career, she has been funded by the National Institute of Mental Health, National Institute of CHD, I don't know, Child Health and Development, maybe. I have no idea if that's what that stands for, but she'll tell us, as well as the Brain and Behavior Research Foundation. And her fun fact is that she loves French bulldogs. And I wish I should have shown a picture of your French bulldog. So cute. She has a 1.5-year-old Frenchie named Hugo. So with that, I bring you Dr. Benedetta Leuner.
Thanks, Lisa. I should have put a picture of my Frenchie Hugo on this slide instead of this. So a couple of things. Can everyone hear me? Okay, great. Can you see the slide in its entirety? Okay, perfect. All right, then we can get started here. I don't know what to do with this thing here. I'm gonna move that off to the side. Okay, so actually, sorry, I'm just gonna make this. I don't know about you guys, but seeing yourself is distracting.
I know, it's hard to know what to do. I keep my video on just in case you want to see me, but you don't have to see me.
Okay. So thanks so much, everyone, for being here. I know we're all probably experiencing some degree of Zoom fatigue at this point in the pandemic, and so I really appreciate your being here. I also wanted to thank Lisa for inviting me to participate in this speaker series and giving me this opportunity to tell you about some of the ongoing research in my lab, which is looking at immune alterations in the pregnant and postpartum brain and how these might contribute to healthy and disordered behavior in new mothers. I know this title is a little bit different than what was originally advertised, but we have some cool new data that I wanted to share, and so I changed my title a bit to reflect that. Okay, so let me get my pointer going here. So as I'm sure everyone here appreciates, females have long been overlooked in neuroscience and other areas of biomedical research. But in recent years, the consideration of sex as a biological variable has grown. And this is a shift driven, at least in part, by policy changes enacted by the National Institutes of Health in the US, as well as other funding agencies across Canada and Europe. So these are some data from a recent study comparing the percentage of research articles, which included only male subjects in blue, only female subjects in red, both sexes in purple here, or did not specify which sex they used in gray. And as you can see, between 2009 and 2019, sex-inclusive research studies that include both males and females significantly increased and did so across a variety of disciplines, including neuroscience. So this greater focus on sex differences is really important, obviously, and it represents a major step forward. But you can also see that perhaps with the exception of reproduction, there's still little research focusing solely on females. And so ultimately questions that are specifically relevant to the experiences that are unique to females are still not well represented in many areas of research. And you can see here that this is especially true for my field, the field of neuroscience. So one uniquely female experience that requires more attention is motherhood. These are some data from a 2018 analysis done by the Pew Research Center, and it shows that in any given year between 1976 and 2016, over 80% of women in the US will have given birth by the age of 40. And so what this suggests is that Paris women represent a significant proportion of the female population, but one that's often overlooked and understudied. The limited studies that have been done to date, however, suggest that current reproductive status, as well as past reproductive history, are linked to health and disease risk in females across the lifespan. And so we shouldn't be ignoring this time period, but instead we should be working more to understand why and how it can lead to differing outcomes in females. So the work I'm going to talk about today focuses specifically on pregnancy and the postpartum period. And these are times of major hormonal changes that will never be experienced at any other time in life. And these hormonal changes are mainly due to the placenta, which is a newly created endocrine gland during this time. So shown here are just a few of the many pregnancy-related hormonal changes in humans on the left, in rodents on the right. And for these hormones, at least, the changes are quite similar. So for both, levels of estradiol, progesterone, glucocorticoids all rise significantly over the course of gestation or pregnancy, and then they drop quite precipitously around the time of labor or at birth. Now, hormonal fluctuations aren't the only dramatic changes that take place during pregnancy, although they're probably the most widely recognized. Shown here are the multitude of other truly unprecedented alterations that occur throughout the female body and in the brain during this time. So this arrow here points to the immune system, which is among the physiological systems that undergoes major changes over the course of pregnancy and the postpartum period. So we all know that the immune system's function is normally to protect the body against pathogens and foreign substances, and it does so by attacking what it identifies as alien and at the same time protecting what it recognizes as self. However, during pregnancy, this task becomes a lot more complicated by the genetically distinct fetus. And so tolerance of this developing fetus requires adaptations in the mom's immune system. And this primarily involves inflammatory changes, specifically shifts in the balance of pro and anti-inflammatory cytokines. So what this diagram here depicts are inflammatory changes across pregnancy, with red showing pro-inflammatory fluctuations and blue showing anti-inflammatory fluctuations. And you can see that after this initial pro-inflammatory environment associated with implantation during early pregnancy, protection of that fetus from rejection requires a shift towards an anti-inflammatory milieu. And that anti-inflammatory state will be present until just prior to delivery, at which point then there's this pro-inflammatory burst that triggers parturition or labor. And then afterwards, after delivery during the postpartum period, inflammatory mediators will mediate healing and involution during the postpartum period. And ultimately, immune changes will normalize in the weeks to months after birth, although there's some data to suggest that some immune alterations can be quite long-lasting and persist even into aging. Okay, so you can see here that these peripheral immune dynamics across pregnancy and postpartum are driven in large part by the hormonal changes I just mentioned. And they're not only important for sustaining the pregnancy and the fetus's growth and development, they're also important for the mom and her health. So if that peripheral inflammatory balance becomes deregulated and shifts towards this sustained pro-inflammatory state with greater expression of pro-inflammatory cytokines, a number of negative physical outcomes may result, such as preterm labor and preeclampsia in the mom, as well as low birth weight or developmental abnormalities in the offspring. Now, again, all of these immune changes are happening in the body or in the periphery, but what about the maternal brain? So importantly, the brain is also now recognized as an immunocompetent organ, but in contrast to the periphery, for which we know a lot about, the brain's immune system has really been unexplored territory within the context of motherhood. And so to address this gap, my lab has been studying microglia, which are the main resident innate immune cells of the brain pictured here. And so today, I'm first going to show you some data from our studies investigating immune changes in the brain across pregnancy and the postpartum period and their relevance to maternal behavior. And then I will present some work we've done suggesting possible central immune system dysregulation in postpartum depression, which is a condition that many new moms experience and which has been on the rise quite significantly during this pandemic. Okay, so given the dynamic nature of the peripheral immune changes I just described, we started studying the maternal central immune system by performing a detailed time course analysis of microglia across multiple regions of the peripartum brain. So as you might imagine, getting brain samples from pregnant and postpartum women can be challenging. So our studies used rats. And we sacrificed these rats during late pregnancy on gestation day 20 or GD20, 1 day and 1 week after birth on postpartum days 1 and 8, as well as on postpartum day 21, which corresponds to the late postpartum period just prior to weaning in rats. And along with these peripartum groups, we also included a group of virgin or nulliparous females without reproductive or maternal experience. And these animals were sacrificed during a stage of their estrus cycle called diestrus 1 or D1. In order to visualize microglia, we used immunohistochemistry for the pan-microglial marker IBA1, and then we performed a quantitative analysis of microglia across a number of maternally relevant brain regions. So we looked at the amygdala, the prefrontal cortex, the hippocampus, the nucleus accumbens, as well as the motor cortex. And we really included the motor cortex more as a comparison region since it hasn't been highly implicated in maternal functions. And so what our data revealed overall was a shift in the neuroimmune environment of the peripartum brain. So shown here are microglia data from the amygdala. And as you can see, compared to virgin females in this first bar here, there's a decrease in microglia on GD20, PD1, and PD8, but a recovery by late postpartum, by postpartum day 21. And we saw a similar pattern across multiple regions, including prefrontal cortex, the accumbens, the hippocampus, but not in the motor cortex. And so these changes appear to be fairly widespread, although the lack of effect in the motor cortex does suggest that there is some degree of regional specificity. Okay, so a critical feature of microglia is that they're highly structurally dynamic. They can adopt different morphologies, which is thought to be a kind of indirect or proxy indicator of their function. So microglia like these here that have these enlarged cell bodies with either few or no branches or long but thick branches are often considered to be more reactive or activated microglia that are engaging in inflammatory signaling. In contrast, microglia like these here that have smaller cell bodies with thin, highly ramified processes are thought to be indicators of homeostatic or surveying microglia, which sample the local environment and engage in low levels of inflammatory signaling. And so given this known link between microglia shape or form and their function, what we did was categorize microglia based on their morphologies. And we categorized them as amoeboid, transitioning, ramified with thick branches, or ramified with thin branches. And doing this, we found that overall thin microglia were most abundant and in postpartum females, shown by the striped bars. Thin microglia were reduced, and they were reduced across the same brain regions. So again, in the amygdala, the prefrontal cortex, the nucleus accumbens, and the hippocampus, but not in the motor cortex. And so overall, we see a significant decrease primarily in these non-reactive surveying microglia, but not a clear transition from one microglial state to another. So an important question to us was how these peripartum microglial changes could arise. And so to answer this, it's important to recognize that in the healthy adult brain, the microglial population is regulated by a balance between microglial death or apoptosis and self-renewing or proliferating microglia. And so given this, peripartum reduction could either be the result of an increase in microglial apoptosis or a reduction in microglial proliferation. And so to evaluate both possibilities, what we did was either label microglia with IBA1 and Ka67 to show proliferating microglia, or we used a different microglial marker called CD11b with a cell death marker called caspase-3, which would show us microglia undergoing apoptosis. And here you can see we found no difference between virgin and postpartum females in microglial apoptosis. However, there was a significant postpartum reduction in microglial proliferation. And so this suggests that proliferation and not apoptosis is likely responsible for that peripartum microglial reduction that we saw. So as I mentioned, microglia engage in inflammatory signaling, and they do so by secreting a host of different mediators, including cytokines, both pro and anti-inflammatory cytokines. And so we wanted to add to our microglia data and start to gain some insight into microglial signaling. And so we measured several different pro and anti-inflammatory cytokines within the postpartum brain. So the pro-inflammatory cytokines we looked at were IL-1 alpha, IL-1 beta, and TNF alpha, And we looked as well at the anti-inflammatory cytokine IL-10. And here you can see no detectable difference between virgin and postpartum females for any of the pro-inflammatory cytokines. However, we did find an elevation, a postpartum elevation in the anti-inflammatory cytokine IL-10. And so there's some other work supporting this postpartum elevation in anti-inflammatory cytokines, including work from Lisa's lab, which has shown that levels of another anti-inflammatory cytokine, IL-4, are also increased postpartum. Okay, so altogether, these data show that similar to the periphery, the peripartum neuroimmune environment is modified, and it's modified in such a way that suggests that the maternal brain might be assuming a protective or inflammatory resistant state. And this appears to begin during late pregnancy and persists for some time postpartum. And we think that perhaps, like the peripheral immune changes, may be driven by hormonal alterations at this time, and maybe even the peripheral immune changes themselves, although we have more work to do on that front to figure that out. I'm a behavioral neuroscientist by training, and so ultimately I'm interested in functional significance and what brain changes mean for behavior. And when considering the timing of these effects, we wondered whether the decrease in microglia in the peripartum brain might be mechanistically linked to the onset of maternal behavior. So there's a growing body of research indicating that microglia are necessary for behavior, specifically for behavioral development. In rodents, it's been shown that early life microglial manipulations in the form of neonatal microglia depletion can lead to disruptions in a variety of behaviors later in life. However, in adulthood, a prominent study which depleted microglia in adult male mice did not observe any substantial behavioral outcomes associated with that microglial loss. And so this has led to a kind of dogma in the neuroimmunology field that microglia in the adult brain don't modulate behavior. It's important to consider, however, that the effects of microglia manipulations in adulthood have not been examined in adult females, nor have they assessed female-specific behaviors like maternal care. And so we set out to examine the role of microglia in the female brain and test their possible involvement in maternal behavior. And we did so using a paradigm called maternal sensitization. So this is a procedure used in virgin female rodents without reproductive or maternal experience, who, unlike postpartum females that have experienced pregnancy, typically don't display maternal care and instead ignore the pups. And that's because these virgin females find pups aversive and they don't find them rewarding. So what you do in maternal sensitization is you house these virgins with foster pups, and you find usually that after about 7 to 10 days, these non-maternal virgins become maternal and will come to display caregiving activities that females who've undergone pregnancy typically display. So now these maternally sensitized virgins show pup retrieval, they show pup licking, they hover over the pups. So again, they display all of the behaviors that are characteristic of normal postpartum females. So what we wanted to know in this experiment was whether recapitulating the decreased microglial tone seen in the maternal brain could accelerate or speed up sensitization in these virgins or non-mothers. In other words, does making the neuroimmune environment of the virgin female look more like a postpartum female or a peripartum female lead to a faster onset of maternal behavior? So to mimic decreased microglial tone seen in the maternal brain, we partially depleted microglia in non-mothers using systemic administration of a drug called BLZ 945, which, if you're interested, is an inhibitor of colony stimulating factor 1 receptor, which is essential for microglial survival. And here you can see in both the images and in this graph here That compared to vehicle treatment, VLZ 945 treatment, significantly decreased the numbers of microglia across several brain regions implicated in maternal care. So decreased microglia in prefrontal cortex, nucleus accumbens, preoptic area of the hypothalamus, as well as the amygdala. And again, these are also the same brain regions where we previously saw peripartum microglial alterations. So then what we did was expose groups of vehicle and BLZ treated females to that maternal sensitization paradigm. And we measured their latency to become maternal. And we considered a female to be maternal when she retrieved, grouped, and licked all of her foster pups within a 30-minute observation period for 2 consecutive days. And much to our delight and kind of to our surprise, we found that partial microglia depletion accelerated maternal sensitization. So here you can see that those BLZ treated females on average took fewer days to meet the criteria for maternal care. We also did a more detailed behavioral analysis, which showed that in that day prior to meeting the criteria for meeting maternal care, the BLZ treated females behaved a little bit differently. So here you can see in gray that the BLZ animals spent less time inactive, and instead they exhibited more investigative behaviors. So they displayed more pup sniffing, shown here in orange, as well as more pup licking, shown in orange, and more pup sniffing, shown in blue. Okay, so less time inactive, more pup sniffing, more pup licking, which might suggest a possible suppression in pup aversion following that microglial depletion paradigm that could have contributed to their shorter sensitization latencies. But this is something we need to more fully explore in some follow-up studies. Okay, so the data I've presented so far demonstrate that there are central immune changes in the maternal brain that might be relevant to maternal brain function. Critically, these changes are also occurring at a time of heightened vulnerability to mood disorders. And so we hypothesize that disruptions to that maternal neuroimmune environment or shifts in the maternal neuroimmune environment could potentially contribute to the development of peripartum mental illness. And the most common mental health condition at this time is postpartum depression. Typically, postpartum depression is experienced by 15% of new mothers, but recent studies suggest that as many as 1 in 3 new mothers are experiencing postpartum depression during the COVID pandemic. Now, importantly, postpartum depression is more than just the baby blues that 85% of new moms experience after childbirth. Unlike the baby blues, which lasts a few weeks, postpartum depression often persists for months and in some cases may be present up to a year or more later. The symptoms of postpartum depression are also much more severe, so severe that postpartum depression is considered to be a leading cause of maternal mortality resulting from suicide. Clinically, postpartum depression is in many ways similar to major depression, with some of the main symptoms being sadness and hopelessness and anhedonia. But in addition to these overlapping symptoms, there are a number of features which distinguish postpartum depression from major depression. So specifically, postpartum depression tends to present with greater comorbid anxiety, about 70% in maternal depression versus 50% in major depression. And many of the anxieties in postpartum depression manifest as fears related to harming the baby. In addition, postpartum depression occurs within the context of a really unique endocrine environment when there are dramatic changes in hormones, as we saw earlier. And then lastly, and perhaps most importantly, this condition strikes at a time when there's the added responsibility of an infant to care for. And moms with postpartum depression may also experience a lack of interest in the baby and difficulties bonding, which can then impair caregiving activities and ultimately adversely affect infant development. And so if left untreated, postpartum depression is not only a problem for the mom and her health and quality of life, but can affect the well-being of the baby as well. So there are numerous risk factors for postpartum depression, which include not only hormonal fluctuations, but also a variety of psychosocial factors, such as a prior history of mental illness, as well as a lack of social support. In addition, one of the strongest predictors for the emergence of postpartum depression is exposure to chronic stress in pregnancy. And this is what we use to induce depressive-like behavior in our rodent studies of postpartum depression. So in our stress model, what we do is expose pregnant female rats to a chronic variable stress procedure. And this consists of randomized daily exposure to 2 stressors. And we do this during the last 2 weeks of their 3-week pregnancy, from gestation day 7 to gestation day 20. Or we have other groups of pregnant rats that we leave unstressed. And then we analyze the brain and behavior from these moms during the postpartum period, typically between 6 and 8 days after birth. Now, importantly, our gestational stress paradigm has little effect on the overall health of the moms and their offspring. So aside from this small reduction in gestational weight gain, the stressed and unstressed groups don't differ in the length of pregnancy or postpartum maternal weight gain. Various pup characteristics are also similar. So stressed and unstressed mothers give birth to a similar number of pups who don't differ in their weight at birth or litter weight gain during that first week of life. However, behaviorally, we have found that gestational stress induces a phenotype in postpartum rats that mimics symptomology seen in depressed moms, including behavioral despair, which we can assess in a paradigm called the forced swim test. So for those of you unfamiliar with the forced swim test, it's a commonly used and well-validated assay to assess depressive-like behavior in rodents, and it's based on the assumption that when you place an animal in a container of water, like the one shown here, it will first try to escape by climbing up the walls, but when the rat learns that it can't, it will give up and exhibit immobility, which is thought to reflect behavioral despair. And this is what we see in our postpartum rats who experience gestational stress, greater behavioral despair, as indicated by more immobility and less climbing behavior. In addition to behavioral despair, postpartum rats subjected to chronic stress in pregnancy also exhibit anhedonia, which is another critical behavioral symptom characteristic of postpartum depression. Here we measure anhedonia with something called a sucrose consumption test. So the sucrose consumption test is based on the fact that rats really like sugar. And if you give them a choice between plain water or a sucrose solution, they will readily drink the sucrose solution unless they're anhedonic, which was the case for our gestationally stressed postpartum rats, whose consumption of sucrose was reduced when compared to the unstressed moms. As I mentioned, postpartum depression is highly comorbid with anxiety in our model. We too find that gestationally stressed moms exhibit greater anxiety-like behavior. So here we used another paradigm, the elevated plus maze, which exploits a rodent's natural aversion to open areas. And we found that the stressed moms spent less time in these open arms and made fewer entries into the open arms, which is indicative of greater anxiety-like behavior. In contrast, stress didn't seem to affect closed arm entries, which suggests that stress isn't producing kind of general alterations in locomotor activity. And then finally, like women with postpartum depression, the effects of gestational stress on postpartum mood are accompanied by impaired maternal care. So here we did something called a pup retrieval test, which basically involves briefly separating the mom from her pups, scattering her pups around the cage before reintroducing the mom to the offspring. And what we found was that the mothers stressed in pregnancy took longer to retrieve all of her pups and group them together back into the nest area. And once they did, they spent less time hovering over their pups in the nest and engaged in less pup licking and grooming. And so various aspects of maternal behavior are also disrupted in this model. And so overall, we think these features like behavioral despair, anhedonia, greater anxiety-like behavior, and maternal care deficits, along with some others that I won't talk about today that we've also seen, like impaired maternal motivation, cognitive deficits, and hormonal disturbances. All of these features make this a good model to investigate the role of the neuroimmune system in postpartum depression. In our neuroimmune studies using the gestational stress model, we've been focusing our attention mainly on the nucleus accumbens, and that's because this region has been consistently shown to be a site of dysregulation in human postpartum depression and in several rodent models, including our own. So in our gestational stress model, one aspect of dysregulation in the nucleus accumbens involves impaired neuroplasticity, which is thought to be an important neurobiological mechanism involved in the pathophysiology of major depression. One form of neuroplasticity that's been linked to depression involves alterations in dendritic spines, which are these tiny protrusions found on the neuron's dendrite that are sites of synapses. So you can visualize dendritic spines in a variety of ways, including with a stain called Golgi. And when we applied this Golgi stain to visualize spines from moms that were unstressed or stressed during pregnancy, we found that the stressed moms had fewer dendritic spines on these neurons in the nucleus accumbens called medium spiny neurons. I'm not going to show the data here, but we've also found that we can reverse the effects of gestational stress on both postpartum mood, postpartum depressive-like behavior, and dendritic spines by treating females with SSRI antidepressants, which is important because it tells us that there might be a causal link between these neuroplastic changes and the depressive-like behavior we see following chronic gestational stress. So within the nucleus accumbens, we've also found evidence for microglial alterations after stress. Here you can see, again, that microglia are reduced postpartum in unstressed females compared to virgins. Postpartum females stressed in pregnancy, however, don't show this decrease. And in fact, they show this significant increase in microglia, which suggests a stress-induced shift in the maternal neuroimmune environment. And what we're trying to do now is figure out if those dendritic spine changes and the microglial changes after gestational stress are related. And we think that they likely are, and that's because microglia have emerged in recent years as important cellular players which regulate neuroplasticity, including synaptic remodeling. And the available evidence to date suggests there are at least two ways they may do so. One is via inflammatory signaling and the release of pro-inflammatory mediators like cytokines. Being macrophages, another way microglia might regulate neuroplasticity is through phagocytosis, whereby the microglia will engulf and digest synaptic elements like dendritic spines. And so the ability of microglia to regulate plasticity in these ways led us to look at whether gestational stress might also be affecting inflammatory signaling and phagocytic tone in the maternal brain. And the short answer for both is yes. So within the nucleus accumbens, we found that chronic stress in pregnancy increased expression of two pro-inflammatory cytokines, IL-1 beta and IL-6. I think these IL-6 data are particularly interesting because there's one study to date that I'm aware of that collected CSF samples from women undergoing epidural anesthesia during delivery, and it found an association between elevated IL-6 in the CSF and depressed mood postpartum. And so our data are consistent with those findings. Using gene expression analysis, we also found that several markers of microglial phagocytosis were upregulated by gestational stress, most notably C1q, which is part of a system called the complement system that tags synapses for elimination by microglia. And we also saw that CD68, a lysosomal marker indicative of phagocytic activity of microglia, was also increased in moms exposed to to gestational stress. And so what we're doing now is we're trying to add to that gene expression data, which suggests there might be increased phagocytic tone in the maternal brain after gestational stress by performing analyses that allow us to directly visualize the extent to which microglia are targeting dendritic spine synapses for elimination. So here you can see one of the images that we're currently analyzing. These are three-dimensional reconstructions which show microglia in green, phagocytic activity in orange, and spine synapses in purple. And I don't have any data to show quite yet because these are very labor-intensive studies that my students are working very hard on right now. But to summarize, these studies show that gestational stress disrupts the neuroimmune environment, the postpartum neuroimmune environment, by increasing pro-inflammatory signaling and phagocytic tone. And this occurs along with dendritic spine loss and a depressive-like behavioral phenotype. So moving forward, what we plan to do is to investigate the extent to which either or perhaps both of these stress-induced neuroimmune disruptions are causally responsible for the behavioral and the neuroplastic changes in our model of postpartum depression. And in these studies, we're using immunomodulatory pharmacological approaches that are targeting each of these aspects of neuroimmune dysfunction. And our hope is that by blocking either one or maybe both, we can ultimately prevent the effects of gestational stress. For now, though, I think that the neuroimmune changes we've characterized broaden our understanding of the maternal brain. They brought in our understanding of the role for neuroimmune cells in the manifestation of behavior via actions in the healthy female brain. And they provide a foundation for us to further explore this connection between the neuroimmune system, neuroplasticity, and postpartum depression. And so I'll end there. I wanted to thank and acknowledge my collaborator at OSU, Dr. Catherine Lenz, and the various students that have been involved in these projects, most notably my former PhD student, Ahi Chaim, who did the behavioral studies and the initial characterization of maternal microglia across the peripartum period. I also have to acknowledge my current student, Courtney Dye, who's examining the effects of gestational stress on the maternal neuroimmune system and analyzing all of those three-dimensional images. I'd also like to acknowledge the various funding agencies that have supported my lab, including the NIMH, where we currently have a grant that is supporting this work. I appreciate your attention, and I'd be happy to take any questions if you have any.
Well, first of all, please let me thank Dr. Leuner for a fantastic talk. And if you, we need all of the encouragement we can get. So those of you that so desire, please use your little emojis to give a little clap if you can. Now we have a lot of people joining us from many different regions in the US, but also I see somebody from Spain and somebody from India online, which is amazing. Really, this is I guess one of the biggest benefits to doing these things on Zoom and the pandemic is that our circles are really widening. So I tweeted, I tried not to tweet about the stuff that you're still working on, but it was so hard because it's so interesting. So please put your questions in the chat if you want, or raise your hand. I'll try and make sure that I see those of you that have questions, and I will ask a question. If not, oh yes, of course, Magdalena has a question. So Magdalena, do you want to go first from Spain?
Hi.
Hi.
Okay, I can go first.
Otherwise, I'll just take up the time, and who wants to hear my questions? Go ahead.
Yeah, this was an amazing presentation. I'm glad.
Thank you.
I've learned so much. I've been taking some notes so that I can study later. So I'm trying to like translate your findings into humans. What my laboratory is finding in humans. So my question is, like, have you done any experiment directly relating these microglial changes and some hormonal variables? Because you, from my understanding, you find these microglial reductions in late gestation in rats. So do you think that this is somehow related to the drop in sex steroid hormones that is occurring during this period? Or it occurs like a little bit before when the estradiol is like peaking, for instance? Because I'm just thinking, like, in humans, we are finding these different patterns, especially before and after birth, more or less. We're like, that's not still real clear, but it looks like during the postpartum, we are finding like increases, but there are also decreases in other periods. And these microglial changes could subserve the changes that we are observing in humans. So yeah, like my question is, if you have an hypothesis on how these microglial changes relate to the hormonal fluctuations that we see.
That's a great question. And we haven't done those experiments yet, but we have some ideas of what might be going on. So as you said, you know, these changes are coinciding with major hormonal changes. We see them during late pregnancy, but admittedly, we haven't looked earlier. So we don't know if they're showing up earlier. But they are present during late pregnancy. And we see the same profile late pregnancy as in postpartum, even though that hormonal environment is very different during those times. So that could suggest a few things. So it might suggest that maybe the hormonal environment of pregnancy is inducing the changes, and then they just take a bit of time to recover after delivery. It could, another possibility is that, oh, I don't know if you guys heard that. My email is alerting me, sorry. Another possibility is that hormonal changes during pregnancy kind of lay the foundation for the changes, and then the changes are maintained postpartum by different hormones. So it's possible that, like estrogen, for example, estradiol could induce the changes during late pregnancy, and then maybe oxytocin maintains them during the postpartum period. It's kind of, you know, akin to what you see with maternal behavior. So you know, those are two possibilities. There's some hormones that are, you know, kind of similar between late pregnancy and postpartum. So like glucocorticoids, for example, are high during both. And we know that glucocorticoids have anti-inflammatory effects. So they could be driving these changes during both times. I think it's highly unlikely that hormones have nothing to do with it. I think they're probably playing some role. We just don't know which ones and how exactly. And I think they're probably not the be all and end all. They're probably interacting with other factors that are changing during this time too. So microglia have receptors for a variety of hormones that change postpartum. They also have receptors for cytokines, and it's possible that those peripheral cytokines, which are also changing, are interacting with the hormones. So, you know, this time period's complex. So I don't expect there to be a simple answer or a simple story. But I do think that you're exactly right, that hormones are probably playing a major role in these changes.
And hormones always play a role.
Yeah.
Stephanie also had a question. Sorry, Magdalena. Sorry.
Hi.
Hi there.
Really enjoyed your talk. This is so cool. I just can't.
Thanks.
So my question is, have you looked at, or do you plan to look at differences with rats that have had a single litter versus having multiple litters? And maybe, like, it seems like the microglia profile sort of returns to baseline after a certain amount of time, but I wonder with multiple litters if there's a more long-term change, or yeah, if you're addressing any of
That's another great question. So again, we haven't looked at that yet. There's too much work to do and not enough people or money. But so I think there are a couple possibilities with this too. So it's possible that this could be something that's, specific to first-time moms. It's possible that this initial change then somehow primes microglia to respond differently, maybe in a subsequent pregnancy. Another possibility is what you suggested, maybe in a subsequent pregnancy, these changes might not only maybe look different, but maybe look the same and last longer. Yeah, I think, I'm not sure which of those seems the most likely, but it's a great question to follow up in future studies. Yeah.
Yeah, thank you.
We have a question from Nisha on sleep deprivation. I mean, in rodent models, probably a little different to do, but is that anything you've ever considered as a possible?
Yeah, it is something that Katie and I have talked about. So yeah, I think one of the things that women most report after having a baby is not, one of the biggest complaints is not having enough sleep. And that could be a contributing factor to the development of postpartum depression as well. I mean, we've not assessed that in our rodent model.
Yeah, it's more difficult.
It's a little bit more
than you think.
Yes. Yeah. I mean, there are ways to, kind of force them to not sleep.
Right. But that's going to be a stressor in and of itself.
It's going to be a stressor in and of itself and disrupts the maternal pup interactions. And so, yeah, it complicates things quite a lot, but yeah.
I have a question, so does Corinne, but she says she's going to type it in, I think, into the chat. Right. So my question is about reducing microglia and showing that pup aversion. So you said you sort of you see this increase in or decreased latency for sensitization or fostering the pup's maternal behavior, which was also super cool. And you made a comment about how, well, maybe this is related to reduced pup aversion. So I'm wondering, is it pup aversion? Is it aversion to other things? Is it increasing the rewarding properties of pup?
Yep.
Are those things that you're thinking about, or?
Yeah. So those data are really tantalizing, and it could be all of those things. So the fact that they're sniffing and licking the pups more, that to me suggests, like I said, that they're not finding them quite as aversive. Mm-hmm. They didn't show any changes in that day prior in pup retrieval. I can't remember some of the other behaviors that would be more suggestive of kind of reward related alterations, but we can't rule that out at this point. So I think we'd have to do some follow-up studies to really tease apart, is it a decrease in aversion or an increase in reward value? I will say that what we also did, I didn't put the data in here, we put them in the open field as well. And the BLZ moms were less anxious. So that could be contributing also to the faster latency. But then we correlated the behavior in the open field with their sensitivities. I can show you actually. I don't know why I'm like.
And then I was just thinking, what about trying to reduce microglia just in the nucleus accumbens? Right. I think
yes, right. So we definitely have to do that next and do more targeted, because the BLZ treatment was systemic. So we're just doing IV injections. Trying to administer it to different brain regions that might have, more distinct roles in aversion or more distinct roles in reward or things like that. So this is that anxiety data. So the BLZ animals are less anxious, more time in the center, more entries into the center. But when we correlate it with maternal latencies, you only see the correlation in the vehicles, but not in the BLZ animals. So I think that these changes in anxiety aren't sufficient to explain the maternal changes in the BLZ. So it has to be something else.
That's super interesting. Yeah, I have to I'm supposed to remind everybody about 2 other events. So I'm just trying to, but another question from the chat is from Karine is, does the type of diet have an impact on the microglia during pregnancy and the postpartum? I mean, you probably didn't alter diet, but.
We did not alter diet in our study, but I imagine, I expect that it might. I do think that there are some studies from, oh gosh, I might get this wrong, but from Stacy Bilbo's lab maybe, and they did do a high fat, I could be totally wrong. I could be just making this up, but
That's okay. I'm not looking it up, so
they might have given a high fat diet, like a Western style diet versus a lower fat diet, and saw immune related changes in the maternal brain. I don't remember all the details of that particular experiment, but one might expect that you would see perhaps shifts in response to diet.
Yeah. Yes, well, that makes a lot of sense because Karine's saying, obviously if you have more high fat or high sugar diets, that might also, and I'm trying to think if I know anything about postpartum depression and diet, which I think there is a tiny little bit, but I don't know that there's not, we wrote about it, but I don't remember. So I'm assuming it's not, I don't know if you remember. I'm getting tons of questions in the chat now. So before I stop though, just so that the network manager, Catherine Moore, won't be mad at me, just reminding you that there's a Women's Brain Health Initiative trainee mentor session on the 22nd with Sarah Monroe. It'll be great on knowledge translation. And on Friday, there's another event for the Women's Brain Health Conference. So, and it's on long-term effects of pregnancy and some short-term effects like cardiovascular health effects as well. So 2 questions from Annie, one question from Annie and from Cindy. Do you guys want to unmute yourself and we'll just go 1 minute longer, 2 minutes longer?
Yeah, I see Annie's question.
Sure.
Can you do focal depletions with BLZ? Yes, you can. And we're planning to do that next, to do, more targeted into the brain to see if we can figure out, where these changes are arising. And then if this is given orally or by injection, we did IP injections, and it is similar to the Plexicon drugs. So the Plexicon are also CSF1R inhibitors. I think
Cindy's question is amazing.
What's that?
Cindy's question is amazing. It's about immune adaptations across pregnancy and the COVID vaccine. And do you have an educated guess on when during, because this question's come up quite a bit actually, in terms of menstrual cycle disruptions and COVID vaccines. Is there a more optimal time to get a vaccine? And would you, I don't know, like during pregnancy, is there more optimal time to get the vaccine?
I don't know. That is a really
Isn't that a good question, Cindy?
That is a wonderful question, and I wish I could answer it. But no, a really, I don't want to steer anybody wrong by
right
giving the wrong answer. So
hopefully they're testing that right
question,
now.
Right? Would the vaccines be maximally?
And does it matter if you're pregnant with a girl or a boy?
Right. Yeah. That's a great question.
All right.
Hopefully someone out there is actually. Congratulations, Cindy.
Hopefully, I know
someone out there is looking at the answer to that.
Well, I think that we could go on and on and on and ask Dr. Leuner lots and lots of questions, but I'm kind of sensed that, we're probably sick of watching Zoom all the time. And then I'm only supposed to have you here for an hour, but if you would all just join me in congratulating Dr. Leuner for a fantastic talk, very clear.
Thanks, everyone. I appreciate it.
Thank you so much. It was really, really great. I'm looking forward to the phagocytosis too.
I know, me too.